All right, good morning. Let's get started. Here's homework 4B. Any more of these? All right. In class on Thursday, we're going to have our second quiz, and you don't need to prepare an equation sheet for that. Any formulas that I'd like you to have available will be provided on the quiz itself. I expect that we'll take about 15 minutes for that quiz, and so it'll be a relatively brief one. And then a week from today, the last homework assignment associated with Chapter 4 is due. And these are questions having to do with Bernoullis equation and rotational flow, which is what we're going to pick up on class on Thursday after the quiz. Any questions related to the announcements? Yes?
So the quiz is going to be after the exam, so no.
That's right. Yeah. It'll cover concepts from Chapter 4. Other questions? All right. Let's look at this animation that kind of explains one aspect of Bernoullis' equation. We know from Bernoullis' equation that in order to maintain a continuity of energy, when a fluid has a increase in velocity, there's a corresponding decrease in pressure. And so this is showing an airfoil as it's intersecting some moving particles that are sort of meant to visualize what's happening over time. And so if you watch the black lines, the black dots, it kind of gives you the idea that the gas that's moving over the top of the airfoil is moving more quickly than the fluid over the bottom of it. And that's what causes that increased velocity is what causes a decrease in pressure over the area of the wing. So that if you know the average difference in pressure over the area of the wing, calculating the lift force is just as easy as multiplying that difference in pressure over the area of the wing. And then that tells you what force in newtons can be lifted by the aircraft. Of course, if the aircraft isn't climbing, then that means that the weight and the lift are in balance or are in equilibrium. One thing I'll point out is that although the fluid velocity over the top of the wing is faster, the transit time isn't equal. And this is a pretty common misconception that ends up not being necessarily true in many cases, that the particles that are here in one line don't rejoin at the same time at the end of the wing. Now, in some cases they might if the velocities are low, but they don't necessarily have to rejoin at the same location. And so it's an acceleration over the top of the wing. Now, conditions here are steady, which means that the flow velocities aren't changing over time. The velocity over the top of the wing and the bottom of the wing are the same. So what kind of acceleration do we have when you've got steady flow but non-uniform? What kind of acceleration is this? What kind of acceleration are we seeing? Convective, right, convective acceleration. So remember, unsteady conditions are associated with a change in velocity with respect to time. That's not what's happening here. Over time, the velocities are the same. It's with position that the velocity is changing. And so that makes this non-uniform flow. And it's convective acceleration that causes non-uniform flow. One application of Bernoullis' equation is a very rudimentary and basic way of measuring a flow velocity. This can be used in a liquid, as is shown on the right side of the screen. So let's imagine that we have a river that's flowing from left to right, and the velocity is the same throughout the cross-section. And as long as we're talking about a relatively narrow depth, that may be true. If we go all the way to the bottom, then of course the velocity is going to be lower. Well, let's just say that there's some range of depth where the velocity is the same. If we have these streamlines, then the streamlines that are above the gauge will just go past it. The streamlines that are below this opening of the stagnation tube will just go under it. But you can see that here at location 1, the streamline that's headed towards the opening of that stagnation tube is headed towards a dead end. So that whatever energy exists as velocity at 1, when that same streamline dead ends at location 2, that energy has to be transformed into something. Now, here's a simplification of Bernoullis' equation where it's written in terms of pressure rather than in terms of head. And we've taken out the elevation term here because both location 1 and location 2 have equal elevation. And so we've just said Z1 equals Z2 and simplified Bernoullis' equation. What the stagnation point has is an exchange in energy. So at location 1, there was velocity. But at location 2, there won't be velocity. And why? It's because an equilibrium has been reached in the part of the tube that's above the waterline. You see this additional height, L? Well, the water level rose to that elevation, and then it stopped rising. It's in equilibrium right now because that additional distance above the waterline, L, represent how much energy was transformed from velocity at 1 into extra pressure at 2. And so this stagnation tube is just a way of physically seeing in front of your eyes the transformation of velocity head into pressure head. So let's go through the equation here. If we say that V2 is equal to 0, and again, the reason why the velocity inside the stagnation tube is 0 is just we're calling it a stagnation tube because there's no flow in it. Initially, when we first dip it into the water level will rise. But then it's going to stop when the pressure, the additional pressure as a result of L, and we know that the hydrostatic equation says delta P is delta H times gamma. Well, instead of delta H, let's just say whatever distance L this is. So it's some incremental increase in pressure. The equilibrium is reached when that additional pressure is equal to how much velocity head was lost as the flow went from 1 to 2. And it's not this entire distance. It's sort of instantaneously that the velocity head is exchanged for additional pressure. It's right at the opening of that tube where that extra pressure accumulates. And so we say V2 is 0. And we can rearrange Bernoullis' equation as is shown here. And what we know about the pressure at 1 over here before the velocity has been exchanged for additional pressure, roughly speaking, we could say that the pressure at 1 is equal to the depth multiplied by gamma. Now, this is where we're on a little bit of thin ice because what do we call this equation? Hydrostatic equation, right? So this hydrostatic equation is valid when fluid isn't moving. But at location 1, the fluid is moving. So it's not static conditions. But it's still a pretty good equation for knowing what's the pressure at 1. You know, since this is open to the atmosphere, if we just are going down vertically, then the actual pressure at 1 is pretty accurately modeled by the hydrostatic equation. So although there may be a slight variation having to do with the fact that the fluid is moving, this simplification, it ends up being fine. So we take it as acceptable that we can find the pressure at 1 by the depth, and here they're calling that parameter D. Multiply D by the unit weight, and that tells us the pressure at 1. So we could make that substitution in here, right? And by that same approach, we could find the pressure at 2. Because the pressure at 2, well, it's just whatever pressure there is at 1 because of the D distance. And then we've got some extra length, L. And so this L plus D is the effective depth at location 2 on the inside of that tube where the stagnation is occurring. So we're applying the hydrostatic equation through the tube up to the surface and finding the pressure at 2. Go ahead.
Why do the pressure at 1 and 2 not different at the same depth on the chemistry?
Why is the pressure different?
Yeah.
It's because at location 2 there's no velocity. Yeah. So the pressure difference is directly related to the fact that suddenly the water stopped moving and that velocity head was lost.
So if the higher system is static, would be the same?
That's right. If the water wasn't flowing, then L would be 0 and the pressures would be the same. And let's say that we have the power to gradually increase the velocity of that river. You know, that we have maybe a valve at a dam somewhere and we're turning it up. Well, if we were doing that, then we'd see L getting gradually larger and larger as the velocity increased. So it's the difference in pressure is because of the difference in velocity. So we're going to combine P1 and P2 into Bernoullis' equation. So both of these equations are hydrostatic, and we're putting the hydrostatic equation into just sort of an algebraically rearranged version of Bernoullis. And this is what we end up with. And you notice we can actually simplify this a bit because we've got gamma times d positive and gamma times d negative. So the gamma times d is going to go away, and what we'll just have is gamma times L. And what's gamma divided by the density? G. So here, this simplified equation, we had the 2 from before. The G is just gamma divided by density, and then the L is left over because it didn't cancel when we removed the D. So we can know this is a crude way of measuring the velocity of a river. I mean, this is essentially a straw, right? This is a straw that you got from Wendy's or something. Dip it down into a river, and you can use that to know what's the velocity of the river. Now, this whole derivation that we've gone through is assuming no energy losses. And the reality is that if you used a Wendy's straw, there'd probably be some energy losses as the turbulence that occurs around the opening of that straw causes a reduction in how high L is. And so it probably would be under-predicting the actual velocity of a river if you used this approach and measured L with your physical system. Isaac?
Why do we not use
The area? You mean like the opening? Where would we use it? Right. Yeah, it's kind of strange. It maybe makes you think, well, if it's this gigantic opening and then it's a really wide straw, could it really lift the water that high? But the distance isn't affected. How high L would get is unaffected by the opening of the tube because the two scale at a 1-to-1 rate. You know, as we make the opening larger, then we're intercepting more energy. You know, whatever velocity there was upstream is being exchanged to an increase in pressure. So the pressure times area is the same as pressure times area vertically once it gets above the water line. Yes? Good question. If anything, I think making the diameter smaller would increase the effect of energy losses because the ratio of how much energy is being intercepted by that relative to the turbulence that's induced. I mean, my theory is that you'd be better off with a large opening instead of a small one, just because the ratio of energy loss to actual energy exchange would be larger with a small tube. But we'd have to put that into the lab to see for sure. We should get some different diameter straws and test that out in lab sometime.
And 90 degrees, because the straw is bent at a 90-degree angle, what happens with...
It doesn't have to be a 90-degree angle. So let's say that it was a 45-degree angle, then it would just be the vertical distance we'd care about.
So it's still the L.
L would be the vertical distance from the water line to the water surface.
And no matter how far that straw is leaned back, it will still go up to L.
That's right. Yeah. Great questions. Very good. All right. So there are some limitations with the stagnation tube. you know how we talked about pitot tubes and how it would be an inconvenient way to measure water pressure in a city, because you'd have these enormous tubes sticking up from the water lines, and to measure the water pressure you'd have to get up 50 meters to see where the water level's at. So we don't use pitot tubes in a municipal network, and a stagnation tube would likewise be inconvenient for use in an aircraft, because a stagnation tube only works when you're measuring the velocity of a liquid and your reference is relative to a gas. Well, in an airplane, the moving fluid isn't a liquid. The moving fluid is air, so it's a gas. And so a pitot tube is a way to apply some of these same principles of stagnation and the exchange of energy from velocity to extra pressure. And so it does that, but it's sort of in a relative system that can be used in a gas-gas environment, relative than just a liquid gas environment. So let's look at a pitot tube. This is a diagram from the book connected to a picture I found online, just to make the point that these measurements are relative. It doesn't matter if this is a top view or if this is a side view. So if this was a top view, then we'd be looking down and it would be horizontally oriented, and that's fine if that's the case. But a pitot tube could also be pointing up or pointing down, and the equations we have for it will work in any of those cases. So location 1 is some opening that is facing the streamlines. And so the stagnation effect is going to occur at location 1. And so what do we know about the pressure at location 1 relative to the pressure upstream of that opening? How's the pressure going to be different? That's right. It's going to be higher pressure at 1 because whatever velocity there was, as soon as it runs into this dead end, that energy that existed as velocity is going to be exchanged into extra pressure at 1. So we've got extra pressure at 1. Now let's look at opening at 2. So it's a circular opening at location 2. The streamline goes past it. It doesn't intercept that opening. That opening is sideways, and so there isn't a stagnation effect. It's measuring whatever the atmospheric pressure is at the elevation we're at, or it may even be that this is immersed in a liquid, and that's fine. Pitot tubes can deal with liquids or gases. But location 2 is just sort of a reference tap. It's an opening where we are measuring the static conditions rather than the stagnation conditions. So, those follow the maze on the placemat at McDonald's? Let's follow the opening at 1 and see where it takes us. If we go through the middle of the pitot tube, all the way around the corner, this is getting fun. All right, here we are, stagnation pressure tap. All right, so it goes into one side of the gauge, and we could call this like the high pressure side. And then the other side of the gauge, and so it's a relative measurement. Whatever measurement we get out of that dial is going to tell us the difference in pressure between the 2 points, between location 1 and location 2. How much is the pressure difference between those 2 points? Because if we go through the static pressure tap, it's kind of like a hollow tube that's encasing this center stagnation tube. It's kind of an ingenious setup that allows us to have whatever the surrounding atmospheric static pressure conditions are is everywhere on the outside jacket of that inner tube that is carrying the stagnation pressure. And so the pressure is high in the center, and on the outside the pressure is less high. Everybody understand the maze there? All right, so this is a pitot tube, and again, it's using Bernoullis equation. This time written in terms of pressure rather than in terms of head, but it's the same equation. It's just sometimes we divide each term by gamma. Now, we can rearrange the pitot tube equation using our definition of piezometric pressure. Remember, P sub z is pressure plus gamma z. And so P sub z1 would be P1 plus gamma z1. And likewise, P sub z2 would be P2 plus gamma z2. And so these are the same equations except for the velocity at 1 is 0 and then making these substitutions. So v1 is 0. And why is the velocity at 1 0? It's because that's a stagnation point. Yeah, the streamline intercepts this location where the air isn't flowing through the tube. The air is in static equilibrium inside the tube. Great question. Well, the velocity that it's talking about, this v2, is just the speed of the air as it slips past that opening. And so if we turned that opening and faced the flow, then there wouldn't be velocity at 2. But because it's not facing the flow and it's just perpendicular to it, then the air, we assume, with no energy losses, the air just slips past it. Now in reality, an actual pitot tube up in an airplane, they know how much energy there's going to be lost at each velocity. And so they've calibrated the wind resistance along the shape of the pitot tube into the velocity that would be read. And in fact, in an airplane, rather than showing pressure on that dial, they just have a airspeed on that dial, because they know what airspeed corresponds to what pressure difference. No, there wouldn't, because it takes some pressure difference to move the needle on that gauge. And so the extra pressure is exerted to get the instrument reading. Good question. All right. So here's the pitot tube equation that it's a really useful way for us to know what's the velocity of flow. Are there any other questions before we dig into an example? All right. Here is an actual pitot tube connected to a Cessna, and so I have reoriented that pitot tube just so that now we can see that it's the same thing here. It's got, the opening on the end. It looks like this isn't the highest resolution photo, but it's got an opening on the side, which is our static opening. And then in here is a series of tubes that goes down into the instrument cluster, and there's a pressure gauge there that's calibrated in terms of velocity. Now, the gauge that it's connecting to can only measure from 0 to 7 kPa. And so what we want to know is, assuming no energy losses, and assuming an air density of 1.2 kilograms per cubic meter, which is the typical air density, then what's the range of air speeds that this setup would be able to measure? And when you solve for the velocities, you're going to get meters per second. So you'll have to do the conversion from meters per second into kilometers per hour, which is what this is interested in. Okay, so what can we say for a horizontally oriented pitot tube like this? What are the simplifications we can apply to Bernoullis equation that's going to make things easier for us? Z1 and Z2 are equal, so they can just be removed from the equation. What's one other simplification we can make? V1 is 0. Right. Great. I think you're headed in the right track. So I'll pause for a moment so you can find out for this pressure differential, P1 minus P2, the maximum pressure difference that gauge can handle is 7.5 kPa, then what's the velocity that corresponds to that maximum differential? All right, if you've got the little sketch, you're always going to get it right if you start off with one of these little sketches. It gets you in the right mindset, that winning mindset. So no matter how bad it is, it helps. So here's 1 and 2, and it looks like the elevations are slightly different, but we're talking in an actual pitot tube like a centimeter of elevation difference, and through a gas, 1 centimeter of elevation difference has such a minute change in pressure that we can ignore the Z effect, and so that's why I'm saying Z1 is equal to Z2. Now, sometimes it's hard just to interpret the problem statement, and if we look back at the words here, it's saying the pressure gauge has a range of 0 to 7.5 kPa. So what that means is that the difference between P1 and P2, the largest that gauge can measure is 7,500 newtons per meter squared. And so I want to look at the extreme end of that. I'm going to say, let's have the difference between the two be that maximum of 7,500. And it doesn't matter what P1 actually is. It may be atmospheric, or if we're going up in the atmosphere in a plane, it'll probably be less than the 101,325 pascals. That's the sea level pressure. But it doesn't matter what the pressure actually is. It's the difference between P1 and P2 that the gauge is measuring. So I'll let P1 be equal to 0. I'm sorry, it's actually P2 is equal to 0, and P1 is the 7,500, because it's location 1 that's going to have the elevated pressure. Between the two of them, one has higher pressure than the other, and it's the location that's intercepting the streamlines. So the delta P set to the maximum, and then we can rearrange Bernoullis equation to make that substitution. So 2 times the pressure difference divided by the density of the gas, square root of that, 111.8 meters per second. Then we go from meters per second into meters per hour by multiplying by 3,600. And then we go from meters per hour into kilometers per hour by dividing by 1,000. End up with 402.5 kilometers per hour. And I think that ends up being faster than a Cessna is capable of flying. So I think that this pitot tube and the gauge will work just great. Any questions about the example?
Can you make more sense of the units to me? I know meters per second is the standard unit turned into.
But why? Yeah. I think if we expand out that newtons, we'll probably get to the bottom of it. So let's go for it. We've got newtons are kilogram meter per second squared. Okay, so this is just our newtons in the numerator, right? And then we've got the meter squared here in the denominator. All right. And now in the denominator we've got kilograms per meter cubed. And so I'm going to leave the kilograms down here in the denominator and move the meter cubes up into the numerator. Okay, so we've got meters to the 4th divided by meters squared. So that's going to be meters squared in the numerator. The kilograms cancel out, and then we've got the seconds squared in the denominator, and then the square root of that ends up giving us meters per second. Sure, yeah. Other questions? All right. Let's make things a little more complicated. Yeah. So this is complicated for a couple of reasons. Number one, it's a liquid going through the pipe instead of a gas. Number two, it's not horizontally oriented anymore. This is vertically oriented, the pitot tube. And since it's in a liquid rather than in a gas, that vertical distance between 1 and 2 can't be neglected. We're not just going to take it out of the equation. We're actually going to keep track of things there. So that's another complication or wrinkle that we have to keep in mind. And then rather than using like a nice little gauge that just has an easy to read scale on it, we're connecting it to a differential manometer. And so it's the deflection here, y, that tells us what the pressure difference is between 1 and 2. Now, we don't have to worry too much because it all boils down to the same principles we've been using before. It's the Bernoulli equation and the hydrostatic equation. Those are the two ideas that go into this problem. And I suggest that we attack this through a certain approach. First of all, it's kerosene that's flowing through the pipe, so we know the SG of that. So we're going to get the density and the unit weight of kerosene from the specific gravity. And then the same thing with this manometer fluid here is mercury, which is often selected because it minimizes the deflection, Y. Since it's such a dense fluid, that helps us out a little bit. So the first thing that it says we want to do is, first of all, write the manometer equation between 1 and 2 through the pitot tube. And then we're going to rearrange it in terms of the difference in piezometric pressure. We've done something similar to this before, where we said, let's start at P1 and then apply the hydrostatic equation, not through the liquid, but through the location where conditions are static. And conditions are static inside the pitot tube and through the manometer all the way to 2. So you sort of trace the route through the center of the pitot tube, then down. By the way, is it the right leg that's connected to the stagnation, or is it the left leg that's connected to that opening at 1? It's the right leg. And how do we know? That's where the pressure is higher. The increase in pressure is pushing down on the mercury more on the right side than it is on the left side, because this right side is the one that's connected to location 1. And we kind of know conceptually that location 1 is the one that's facing the flow, and it's where that extra velocity is being converted to an increase in pressure. All right, so we're going to start at 1, where you do this sort of thing, P1 plus, and then we look, all right, we're going to go down some distance. The distance we're going to go down is Z1 minus Z2, and multiply it by the unit weight of kerosene, so gamma kerosene. And then, so that now we're at location 2. We still need to go down further. We need to go down L now. So plus, since we're going down, L times gamma of kerosene, and so on until we say is equal to P2. All right? So I will show you the and so on later, but I don't want to show it all to you because I want you to think through creating this equation and then rearranging the equation, the left side of the equation, so that you've got P sub Z1 minus P sub Z2 is equal to something. So you rearrange it in these terms because then once it's rearranged this way, this is the hydrostatic equation with the manometer, we're going to stick that into Bernoullis equation. And that's what this is at the lower bottom of the bottom left of the screen. This is just Bernoullis equation. We've rearranged it because this is often what goes into the pitot tube formula. Combining the two ideas. All right, so let me stop talking. I'll pause the recording and give you some time to rearrange the hydrostatic equation to find out what's going on with the manometer and then solve for V2. That's really what we're trying to find out is what's the velocity of the liquid going through the pipe if Y, the deflection, is 18 centimeters. Then how quickly is that kerosene moving? Okay, I've just put the manometer equation on the screen there. I think most people have the basic idea of like what we're trying to accomplish. You can see what I did is I sort of moved everything together because I have in my mind that I want to have P sub Z1 and then P sub Z2. And so I sort of arranged things here, the P1 and gamma K times Z1. And then I've got the P2, which I moved over from the right side of the equation so that it could be next to the gamma K times Z2. And that's ultimately going to be my P sub Z2. So all that's on the left, and then what's on the right will be the gamma mercury times Y, which I moved over to the right, and then the gamma kerosene and Y, which is moved over to the right as well. Since they both have a common Y, and I end up with y times gamma mercury minus gamma kerosene on the right. And so like what's the whole point of coming up with this expression on the right is that then that's what we can drop into the Bernoulli equation, this one. So we're going to put, we can either calculate the value that you get from y times the difference in the unit weights, or you can just put the equation itself into Bernoulli equation. So if you take that approach, here I've made the substitution. I start off with Bernoulli's equation on top, and then I say, well, instead of writing it as PZ1 minus PZ2, I'll just take the result of that from the hydrostatic equation and make a hybrid. So now what I've got here is the hydrostatic equation inside of Bernoulli's equation. And the hydrostatic equation was relating the difference in piezometric pressures by the deflection. And so you have to remember, what is piezometric pressure measuring? Piezometric pressure measures the difference in pressure, and it also keeps track of elevations. So the pressure at 1 and 2 is going to be different because they're at different elevations, right? But we don't care about the elevation effect of the pressure difference. We want to keep track of the pressure difference that arises out of the fact that 1 is intercepting the streamline and 2 isn't intercepting the streamline. And so this deflection y has nothing to do with the fact that 1 and 2 are at a different elevation. This deflection is entirely because of the fact that 1 is facing the flow and 2 is sideways to the flow. In other words, that location 1 has that velocity exchanged into extra pressure. So that extra pressure that's at 1, the velocity head, this deflection y is a physical manifestation of the velocity head that exists in the flow. So if I go back to the solution then, once I've made that substitution and jam the numbers in there, for some reason when I was doing the calculations I used 13.6 as my unit weight. So if you use the correct value of 13.56, then I think you get 133.023 instead of 416. And so there will be a slight difference in the numbers you get. What was the velocity if you use the correct stated unit weight for mercury? 7.69 instead of 7.47. So I apologize for the mistake. Next semester it'll be fixed because I changed my slide to the lazy, rounded off version of mercury. But does everyone understand the basic approach here?
I got 7.46 and I used the 13.56.
Oh, really? Well, I don't know what to believe then. All right, let's look at some key ideas for the homework. We've still got 5 minutes till class is over. So I want to look at a similar problem to what we just solved. This is easy though, because it's a, these are piezometers rather than a pitot tube. All right, so these piezometers measure piezometric pressure. That is, the elevation of the water gives you an idea of what the pressure is, where it's connected. So there's a difference in elevation of 6 inches. Ooh, like traditional units. We feel icky already, right? 6-inch deflection. So where is the pressure higher? At 1 or at 2? Where's the pressure higher? Maybe it's hard to see because the lights. Well, that's where the water level's lower. So that's not right. Thanks for playing, though. All right, so we've got high velocity at 2, although that's a bad diagram because it looks like that arrow's short, right? Let me make it even longer than the other one. They make it hard to outdo the length of the first arrow. But, all right, so the velocity is really high at the center, and the velocity is lower here because it's got a bigger cross-sectional area, right? So just as a reminder of how these piezometers work is that if there was 0 velocity through this device, then the levels would be equal. But then as soon as we start putting flow through there, the velocity at the throat is going to be higher than the velocity at the entrance to this venturi. So the velocity of the entrance is 10 feet per second. We don't know what the velocity at the throat is. That's what you have to calculate. But what we do know is the difference in pressure between the 2 points. And actually, piezometric pressure, because this difference in pressure would be affected by the fact that they're at different elevations. But the piezometer allows us to say, ignore the fact that they're at different elevations. We want to know what's the difference in pressure that's related to the difference in velocities. So we're going to do that same grouping by P sub z as the example that you saw today in class. And so it's a combination problem. It's a combination of hydrostatic equation and Bernoulli equation, similar to what we just went through. All right. With that said, we are out of time. One last quick look at these announcements here. The next thing on your calendar is a quiz on Thursday. So I'll see you on Thursday for that. Have a good one.
Just one question.
Probably.